Okay, so look into nuclear energy this time, and that's I think chapter 15 in your textbook. So in our country, United States, nuclear power, it's been a controversial issue, right, for some generations. People are kind of skeptical about it because of its risk. But in Europe and in Japan, okay, they use nuclear power because they need it. And of course, we've got like big disasters, right, because of the system design was poor, right, and also operation, right, operation failures, because some employees, right, don't know how to, or maybe they didn't get enough training, right, so it can mess up, right, the system. Usually employee mess up the system, but for nuclear, it's you can't mess it up so much, right? It can go into very big disaster. Your Fukushima, your 3 Mile Island, your Chernobyl, right? These disasters are your nuclear system failure, and also, of course, human error. So nuclear energy, where's my highlight? Okay, so nuclear energy, we are gonna extract the energy out of nuclear fission. That's just a chemical reaction, okay? And we're dealing with the atomic level process, okay? And like I said many times ago, small things that we can see, all right, inside of a lot of the matter, if you can be able to process them, they generate incredible amount of energy, just like sun, okay? So if you take a look at the fission, it's just a reaction, okay, nuclear fission. So we've got just a process, and in that process, you are splitting a nucleus, okay? So you go back to your atom, so atom has a nucleus, and atom has electron, okay? And so this place. So that nucleus is going to split, right? And here is a better picture, right? The split, okay, into two nuclei. And of course, the original nuclei, right, nucleus split into two, so therefore you've got smaller masses, okay? So fission, you need a very, of course, atomic level, you need a bigger, okay, above 90 nuclei they got to be big, okay, in order for them to be able to go on nuclear fission. So you can remember fission as splitting, yeah? And they're gonna split and split and split, and we call that chain reaction, okay? Just an ongoing series of splitting reaction or fission reaction. So billions of reactions happen, right, every second in a chain reaction. So in the nuclear reactor, what's going on? That's going on inside at the atomic process, yeah, level. This is just showing you a picture for chain reactions, but you already understood. Start with a very large nucleus, okay, splitting into two masses of nuclei, right? And then we do it again, yeah? Okay, so at the facility, right, nuclear fission reaction is happening in the reactor. You can control the chain reaction, right, in there to generate the electricity. So uncontrolled, I'm going to highlight it here, uncontrolled chain reaction, it can take place during the explosion, okay? This is just an atomic bomb where your atoms are, and these atoms are undergoing the nuclear fission. So we're actually talking about the nucleus inside of these atoms. Byproducts, very bad. That's why people are very skeptical about nuclear reactor, because it is radioactive. It's not good for human health. But environmentally it's healthy because energy, right, we got from the nuclear reactor doesn't come with the emission, yeah? Because energy from fossil fuel that comes with the emission. However, now no system is perfect. It does create radioactive stuff. Okay, then we will get into fusion. So after fission, we're gonna fuse. Fusion is the opposite of fission. Fission is splitting, and fusion is combining. Okay, so we're gonna combine two smaller nuclei right into one large nuclei. Here we just talk about atoms, but the nucleus is inside anyway, and you've got your don't forget you have your electrons, all right, in your atom. So we're getting the electricity out of it. Electricity, don't forget your current, which is your I. Current is your electrons flow, okay? Don't forget that as well. So that's your, I'm just going to write a negative part of your atom, okay? So E minus, you now know what we're doing. Yeah, we're trying to get this out of the atom by splitting or combining. So nuclear fusion reactions, we also call them thermonuclear reactions, okay? Fusion, combine, fission, splitting, combining the nuclei, splitting the nuclei, okay? Okay, so fusion reaction, they exist in all the stars in the universe. So sun is a star, right? It's a good example for the nuclear fusion reaction. When they wrote this, all right, textbook, this text was a little bit old, right? We have a breakthrough already for the fusion reactor. So it just here this section is just telling you that it's a little bit difficult, right, for creating the fusion reaction on Earth here, because you need like extreme temperature, and this temperature we can come up with this to accommodate it. Okay, that was 100,000 and 1,000, so it's Celsius. Okay, so that's really high, not even Fahrenheit. It is in Celsius, so you can imagine how hot that is. And here is just a little video just showing you your fusion, nuclear fusion and process, and you can see fusion behind him, alright? Just fuse, two nuclei fuse into one. And here's just a displaying the reactor facility, okay, in there. And this reaction is, we call it the nuclear fusion reaction, okay? Two nuclei fused, get a bigger, larger nucleus, okay? And we get the neutron out of it, and there's a helium. Not limited to only helium. We have many different types of fusion, okay? And you'll get a different element. So nuclear reactors, you can see right there, they are built right to sustain a controlled nuclear fission reaction. Because the fission reactions are they're dangerous, all right? And it depends on the scale that we want to do. Your reactor got to build, all right, very carefully. So main components, nuclear reactor, we've got reactor vessel, we have tubes, okay, for uranium, and we have control rods, and then we have containment structure. And this is the most important thing in the reactor, okay? Because if this system is not perfect, you're gonna have leak of radiation, and also explosion can happen. This video is just showing you the fusion reactions inside of the nuclear reactor, okay? Okay, so for nuclear reactors, there are two different types of nuclear reactors. So we have pressurized water reactor and we have boiling water reactor, and we will get into this too, okay? So both of them, they use a nuclear, I'm going to highlight it right here, fission, right? And since we're using water, look at that. In both types, we gotta heat that water, and then we're gonna produce a steam. Okay. Okay, then we'll take a look at R2, alright? Nuclear reactor, the same thing. Here, pressurized, and this one is a boiling water. So we do the same thing, right? Here's your reactor vessel, your reactor vessels. We're gonna heat the water, and it will turn into steam, your water vapor. We're gonna use the steam to run the turbine, yeah? Same thing right here. And then we're going to run the generator, same thing right here. And then electricity, you got it to your house, you got it to the city, okay? And excess steam come back here. Yeah, we have a cooling system. Every time you see condenser, that means you're cooling back down, and then turn that steam back into water, and then do that again. Yeah, it's a pretty simple system. These two types of, I want to say, like nuclear reactor is different from. There is another type that we don't use here in the U.S. Right, the direct in using the direct reaction, your fission or fusion. Okay, those types of reactors are not very popular here in the United States because we think that it isn't very safe. Okay, but using the water, okay, and use the vessels, reactor vessels, to heat the water up, and that kind of design is less risky. Okay, so therefore we use these two types. Okay, so fission in the reactor vessel, we got heat. Use the heat. Heat the water. We got steam. Use the steam. Turn the turbine. Run the generator. Produce electricity. Okay, excess steam. Cool it back down in a cooling system. We call it, the name is condensation. Turning the steam back into water. Okay, and then use it again. The United States, these are just the numbers. 31%. Okay. Compared to worlds of course, nuclear power, we use 31% only, and we consume 22%. We have 440 nuclear power, okay, reactors all over 31 countries in the world, and they account about 16%, okay, of the world's global electricity. All right, more information. This is 2016 data. United States, okay, electricity generation. TWH is nothing but just a unit, so go by the terawatt hour. So 4079 TWH, so terawatt. Every time we say terawatt, meaning that there is hour in the back, okay? So that's just like how we call it. So 4079, so 4079 terawatt, 1380 terawatt, okay, that's a 34%, okay, from gas. 1240 terawatt, that's 30% from coal. 805 terawatt, that's 19% from nuclear, okay. 266, that's from hydro. 226, all right, from wind. 117 from other stuff. Yeah. So for nuclear, I'm gonna highlight it right here for you. It's about 19 and 20%. Yeah. Okay, more information. We have 65 pressurized, all right, water reactor. So pressurized it here, and your two the diagrams. So that's PWR, so pressurized water reactors. Yeah. Combined capacity 64. Okay. GWE. So GWE is again is another unit, right? Dealing with the power. So electric power. When we say power, that's electric power. We call that the Geiger for G, and then W is for watt. You will see a little bit of difference. Sometimes we use this W big one, right? Big W, and then little E for electrical. So GWE. Okay. That's your Geiger word, electrical. I would write it, I don't know who write this one, it's supposed to be like this, okay? Here we go. This is the correct way of writing it. Anyway, so there are about 34 boiling water reactors, so that's your BWRs, yeah? Combined capacity is 35, right? GWE. Gigawatts. I just say gigawatts, so that's electrical. US nuclear, all right, generating capacity. They come from the reactors, meaning your nuclear reactor. And these reactors were built between 1967 to 1990, okay? So we usually use uranium. This is just a type of uranium-235 in nuclear reactors, and you can write U, all right, abbreviated uranium-235. So 0.1% in nature, and about 3%, right, to produce the reaction. And we got them in rocks, right, submerged in the water. That's just a containment. Uranium-235 is very radioactive, so therefore we have to handle it with care, okay? So therefore people are skeptical about the nuclear power plant, okay, because of this, yeah? So we have to make our system, all right, and our safety is the most priority. And environmental concern, we don't emit, right, emission. I mean, like pollutants doesn't come from the nuclear power plant. The only thing, right, that is risky is the radioactive byproduct. Okay, so talking about safety, and we'll get into the disasters. So we have 3 known disasters in the world, and one is the 3 Mile Island. All right, that's here in the United States. Happened 1979, Harrisburg, Pennsylvania. The other one is in USSR, Russia, right? Soviet Union at that time, 1986. Your Chernobyl, and then we have Japan in 2011, Fukushima, okay? Location. So I think this is Three Mile Island, and this one is Chernobyl, and then that's Fukushima. Okay, Chernobyl is the worst, right? Nuclear power plant disaster. So we have issue in design, we have issue in human, right? Error, so that's operator error. So they didn't do their power check, safety power check, and then that escalated all the events. Yeah, it's kind of like a domino, like I say many times. System, all right, is connected with so many parts, all right. When we talk about system, you got parts, and you have processes, right, connected to each other. So you don't want to mess up anything. If you mess up something, all right, and if we don't have a backup system or the repair, all right, automated repair, then the entire system can go down. People try to, like mess up with the electric grid as well, right? Evil people, bad people, they do it. But then for electric grid, we have automated repair, right? We call it the smart maintenance, and they sense. And some of the system, all right, sections are completely they can be able to detach, all right, itself, right? So that way, if something happened here, it won't affect the other one, and you can go ahead and quickly repair it. Okay, so these are the maintenance technology and maintenance major got to learn as they grow into their career. Okay, so right now at school, you're getting the basic foundations of that, but you can build upon that knowledge and get on with any kind of system or applications, all right, or technology that you will be using in these plants. Okay, now, so what happened to Chernobyl accident is it's cascaded, all right, all the way, and it get to the core and they get the worst possible explosion right there. Yeah, well, that's in Russia. Okay, so let's go to the next one. So about 250 million people get, right, exposed to the radiation, so that's pretty bad because radiation can alter your DNA, which is your genetics. So if you plan to have family and children, then this kind of radiation can affect your future generation. Okay, and about 60, all right, died in that accident, and 150,000 got serious, all right, radiation exposure. Radiation exposure, you can't know it right away. These are like, it takes time, okay? But one thing true about radiation exposure is they're not always negative. Some of them are, they create a human, all right, genetics in a way that they have some form of, what should I call it? Some form of ability, okay? So like in Japan, the atomic bomb, right, created generation, and one of the generations, like people in that group can be able to do mathematics by mind. Okay, so that's one of the effects coming out from the radiation, even if they appearance or get affected very badly, seriously. So some of the Japanese generation, they don't look good because the genetics DNA got altered because of the atomic bomb, right, radiations. But somehow the brain got very good. Okay, so that's good and bad happening. Yeah. Serious, they become very intelligent for some reason after 3 or 4 generations later. Yeah, so we can really say that radiation exposure are always negative because some of the good things can also come out of it. We get into US, right? Nuclear plant 3 Mile. So what happened to them? The malfunction was your valve, right, in that system, and then they lost the coolant, because of the meltdown, right? So right now you don't have to know in details, all right? If you get like, okay, something happened in the system that caused, all right, the accident, and it is above for the 3 Mile Island accident, okay? And we have some radioactive gas, okay? There was no fatalities, so that's a good thing about it. They have reported, all right, no significant increase in cancer or death in exposed population, but this is very skeptical because of the, like, we don't know. They actually research on it or track, all right? These things are, you have to track from generation to generation. You can't just track the current exposed generation. You have to track the generation after that exposed generation, okay? So there's some skeptical, like arguments, controversies going on that effect after the explosion. So just showing you a 3 Mile Island picture. Fukushima, so the next accident. So they've got 6, separate nuclear reactors. And they're actually using the boiling water type. So what happened was they get the large earthquake came and the tsunami, right? So if you think about Fukushima reactor accident is not human error. It was a natural disaster, okay? Tsunami hit it and flooded, right? And that's back in 2011. So 2011 is not a good year, right? So we in the United States, there's no terrorist action going on, right? In New York, and in Japan, we got Fukushima stuff. So radioactive, right, waste, very deadly, right, went off with this flood, of course. And then flood is your water, right, connected river and streams into the ocean. So that's a pretty bad thing. So fish won't like that. And anyway, still ongoing research, right? Who got affected, what got affected. And again, the ocean is going, the water currents is going all over the world. So it won't be localized in Japan. It will be spread all over the marine life, right, in the ocean. So anyway. Okay. So out of their 6, alright, nuclear reactor, they got 3 down. And they were able to contain, right, and then cool down the system before the catastrophic damage took place. And this Fukushima accident is the most, alright, complex nuclear accident, of course, because of the force of tsunami is really extensive. And all of that units will happen like in the same way. So if you compare to Chernobyl accident, alright, it's more complex, right? Even if Chernobyl is the #1 of the worst, right, accident because of the fatalities, the complexity of Fukushima, right, reactors, because 3 down out of 6, that's more complex than the Chernobyl accident. For Chernobyl, they've got only 1 reactor down. Okay. Okay, so here we're looking at the risk. It's just a table. And from coal and nuclear powered electricity generator. And we have hazard type right here, coal, and then we're going to compare that to nuclear. Yeah, I'm not going to read everything, so I just want you to go ahead and study. All right, hazard type between the coal and the nuclear. Okay, and here with a little star right there, and there is a description for that. Yeah, and that's just a death comparison. Okay, death counts. And you separate by routine occupational hazard, you have routine population or hazard, you have catastrophic hazards, you're excluding the occupational right here, and then your general environmental degradation. Okay, so make sure you get this table. Okay, and I'm going to list that out for you so it is easier, okay, to study. Okay? So nuclear power is competitive, right, with natural gas. So that's pros, and definitely non-polluting, no emission. It doesn't contribute to global warming, right? Another good thing. Obtaining the fuel, and it takes only like 5% of the energy output. And it also creates enough electricity, and this is the most important thing because we're looking for the profit anyway, to power like 1 million homes, okay? And that is like per nuclear reactor. And here is our last slide, and the same thing, we're giving you some links for the video. Don't limit yourself to these links, alright? You can Google them for more video to support your learning. These are pretty good, alright? Like how nuclear energy works, I like that video. And this one is also not so bad. But you might find it a little bit bored to watch it. Of course, don't limit yourself with only these links. Okay, so I'm going to go ahead and stop right here.